Hello everyone and welcome to our channel Mootechie. It's a pleasure to have you here, whether you're a student, a professional in the field, or simply passionate about the science behind the materials we use. Today we're diving into a fascinating topic that forms the backbone of manufacturing and engineering. So let's get started. Now let's begin our journey into the world of the heat treatment process. Moving forward, we'll see how the world of metals is broadly classified. We have two main families, ferrous and non-ferrous metals. Under ferrous, we primarily have steels. Now, the non-ferrous category includes metals like aluminum gori, aluminum alloys, titanium alloys, nickel-based alloys, and cobalt-based alloys. But let's focus on steels for a moment. Steels themselves are categorized into plain carbon, alloy steels, tool steels, and stainless steels. And an interesting side note for non-ferrous metals: some, like certain aluminum alloys, are non-heat treatable, while others are heat treatable. Coming up, we'll discuss the different types of steel in a bit more detail. We have carbon steel, alloy steel, stainless steel, and tool steel. Drilling down further, carbon steel can be low carbon. Stainless steel has several types, including ferritic, martensitic, austenitic, duplex, and precipitation hardening types. This leads us to a common and important comparison. Let's look at type 316 and 316L stainless steels. So what's the difference between SS 304 and 316? Well, we're focusing on 316 here. First, standard 316 stainless steel. It contains more carbon. This makes it more liable to weld decay, but it is very effective in acidic environments. Now, its counterpart, 316L. It contains less carbon. This makes it better for avoiding weld corrosion, and it's good for high temperature, high corrosion use. It's all about finding the right balance for your application. As we continue, let's understand the key properties we look for in these materials. This slide shows us a whole web of mechanical properties. We have stiffness, stealth, weldability, castability, conductivity. Though it's written as electricity, the intended meaning is electrical conductivity. Formability, mechanical properties, plasticity, creep, ductility, brittleness, malleability, hardness. Each of these tells us something unique about how a material will behave. Now, to understand many of these properties, we need to grasp a fundamental concept: stress versus strain. Imagine a force being applied to an object. Stress is defined as the force divided by the cross-sectional area of the material. So it's force over a specific area. Now, what does this force cause? Deformation. And strain is the measure of that deformation. It's calculated as the elongation, or the change in length, divided by the original length. So a force causes stress, which leads to strain, or deformation. Let us now look at a key property: elasticity. It is defined as the property of a material to regain its original shape after deformation when the external forces are removed. Think of it as the power of the material to spring back to its original position after the stress or load is gone. This is also called the tensile property of the material. Now, this deformation can happen in different ways, what we call differential stress. The main types are tension, which stretches the material, compression, which squashes it, and shearing, which causes parts of the material to slide past each other. The fundamental idea here is that any body subjected to a force will be deformed. It's how it responds that matters. This brings us to a crucial visual concept: elastic and plastic deformation. Imagine a graph with stress on the vertical axis and strain on the horizontal axis. Initially, as you increase stress, the material deforms elastically. It will spring right back when the stress is removed. The line on the graph goes up, and if you reversed it, would come straight back down. But there's a point, called the yield point, where the behavior changes. After this point, the material begins to undergo plastic deformation. This is permanent deformation. Even if you remove the stress, the material will not return to its original shape. It stays stretched or bent. So on the graph, you see the line curving and continuing upwards even after the stress is released, indicating this permanent change. Let's now define some of these properties more precisely. Brittleness is the property of breaking without much permanent distortion. In other words, a brittle material just snaps instead of bending. It's the complete opposite of ductility. Ductility. A metal is ductile when it may be drawn out in tension without rupture. Think of drawing a metal into a thin wire. A ductile metal must be both strong and plastic. The script notes that lead wire is difficult to draw, not because it isn't ductile, but because its strength is so low. Strength. Quite simply, the strength of a metal is its ability to resist the application of force without rupture. It's about how much load it can bear. Plasticity. This is a rather similar property to malleability. It involves the material undergoing permanent deformation without rupture. Malleability. This is the property of permanently extending in all directions without rupture, by pressing, hammering, rolling, etc. It requires the metal to be plastic but is not as dependent on strength. A great example is lead, which is a very malleable metal. Moving forward, let's look at a few more essential properties. Elongation. When a material is pulled in a testing machine to find its tensile strength, it stretches before it finally breaks. The elongation is the amount of this stretch and is generally expressed as a percentage of the original length. Let's understand this with an example. If a test length of 50 mm stretched to 69 mm before fracturing, the elongation would be 69 minus 50, which is 19 mm. Then the percentage is 19 divided by 50 times 100, which equals 38%. A good elongation percentage indicates a ductile material. Hardness. The hardness of a metal is a measure of its ability to withstand scratching, wear and abrasion, indentation by harder bodies and marking by a file. It's essentially the material's resistance to surface deformation. Toughness is the amount of energy a material can absorb before it fractures. It's like the material's ability to withstand a sudden impact. And finally, let's wrap up with 3 more critical concepts, especially when considering high-temperature applications. Creep. This occurs when a metal part is subjected to a high constant stress at a high temperature for a longer period. It will undergo a slow and permanent deformation, often in the form of a crack, that may grow and lead to what we call creep failure. Resilience. This is the property of a material to absorb energy and to resist shock and impact loads. It's measured by the amount of energy absorbed per unit volume within the elastic limit. This property is absolutely essential for spring materials. Fatigue. A material can fail at stresses below the yield point when it is subjected to repeated cycles of tensile and compressive stresses. Think of bending a paperclip back and forth until it breaks. This type of failure is known as fatigue. And that brings us to the end of our session on the heat treatment process and the properties of metals. Thank you for your attention and your passion for learning. We hope this has been an enlightening session, giving you a clearer understanding of what makes materials strong, durable, and suitable for their specific tasks. Thank you. See you in the next class. Author Mootechie. End script.